So in this section, we are going to utilize a specific circuit example, which we choose the CPM buck converter to calculate its CPM transfer function and compare the difference of transfer function with the conventional pulse width modulated controller. So CPM buck example. So first, let's plot the small signal model for the buck topology. So here is the small signal line input, and here is the independent current source, which is controlled by the controlling signal, right? And here is the virtual AC transformer. We use a wave line to denote that this is a AC virtual transformer. On the secondary side, the turns ratio equals to 1 to D. On the secondary side, we have another independent voltage source, which is also controlled by the duty cycle, right? VG times D cap. And we have the low pass filter network. CLR. So here is the inductor current, IL. And here is the output voltage. So based on this small signal equivalent circuit model for buck topology, right, we can list the expression of several critical transfer functions, right? For example, the GVD. GVD is equal to V over D times 1 over denominator. So where the denominator here is a like second order equation, right? So it equals to 1 plus S L over R plus S squared LC. And so basically GVD is maintain a quadratic pole response, right, due to the second order part in the denominator. And secondly, we look at the GVG transfer function, so which equals to D times 1 over denominator. So which is also a quadratic pole response. And thirdly, we look at GID, meaning that how the controlling signal D affect the inductor current, right? So this will be equal to D V over D times R times a fraction of 1 plus SRC divided by denominator. So this is a quadratic pole response plus a left half plane 0, right? And last one is the GIG, meaning how the controlling line input, right, affect the inductor current. So this will be equals to D over R times the same fraction of 1 plus SRC divided by denominator S. So based on those coefficients, right, we can first try to derive the control to output the transfer function. So basically, we have derived in the previous page of the blackboard. Here, I will just rewrite it. So basically GVCS will be equal to a fraction of Fm times GVD divided by 1 plus Fm times GID plus Fv times GVD. So for Bach topology, the Fv coefficient is 0. So this part is gone, right? Then we can insert the GVD and the GID into this fraction to obtain the complete expression. So here will be fraction of Fm times GVD, which is V over D, 1 over denominator, 1 plus Fm GID, which is here, right? We insert this to here, V over dr times 1 plus SRC over denominator square. Okay, so next we can simplify this expression, right? Basically by multiply both numerator and the denominator by den S, right? By den S. Simplify. So GVCS will be equal to Fm V over D divided by, here is denominator S plus Fm times V over dr, 1 plus SRC. So we will see that because denominator is a second order expression, right? After inserting denominator here, we will see that this again is a quadratic pole response, right? Quadratic pole response. So meaning that we can normalize this transfer function. So to be the standard format, GVCS equals to, so the numerator will be a DC quantity, right? So we denote as GC0. And the denominator is a second order part, 1 plus S over QC omega C plus S over omega C square. So by comparing the normalized format and the complete expression, we can map those parameters one by one, right? So first, let's look at GC0. GC0 will be equal to V over D times the fraction of Fm over 1 plus Fm times V over D times R. And secondly, we compare the second order term to find out the expression for omega C. Omega C will be equal to 1 over square root LC times square root 1 plus Fm V over dr. Thirdly, we compare this first order term to solve the quality factor. So basically, quality factor will be equal to R times square root C over L times the fraction of square root 1 plus Fm V over dr divided by 1 plus RC Fm V over dl. Okay, so now let's look at those three parameters. If you still remember for the PWM Bach converter, we also have a quadratic pole response, right? But the p-domain converter, the coefficients are like v over d, 1 over square root LC, and r times square root C over L. So the difference are this part. So namely that the circled part corresponds to the CPM impact. To the control to output transfer function. So if you look at those circular parts, you will see that basically the Q is reduced. So CPM impact reduces the Q factor of poles. And also, if we consider that the fraction part is much larger than 1, you will see that the circular part is proportional to 1 over square root FM. Mainly because denominator has a FM term and the numerator has a square root FM term. So that we will have roughly the QC proportional to 1 over square root FM. And as we noted that the Q is reduced, right? So in comparison with p-domain. So basically this means that the poles, the two poles, a pair of poles becomes real and will separate it. Will separate it. So then we consider we adopt the low Q approximation for the quadratic pole response. If we consider Q is sufficiently small, so basically we can decompose the two poles. One is the low frequency pole, one omega LF. So this will be equal to quality factor times the omega C. Then we insert omega C and Q to here, right? So you will see that we can obtain the low frequency pole expression as R over L times, so this square root times square root, the square root sign is removed, right? 1 plus FM V over dr. And for the denominator, it will be just this equals to this denominator, 1 plus and regarding the high frequency pole, so will approximately be equal to Q omega C divided by QC. If this assumption is valid, right? If this assumption is valid, low Q. Then we insert the omega C and the QC to here. So you will see that the square root term is cancelled. So this will be 1 over RC times this part, 1 plus RCFM V over dl. And if we consider that FM, if FM is large, for large FM, the pair of poles can be further simplified, right? Simplified. For example, now let's consider the time domain frequency with F low frequency. So will be approximately equals to 1 over 2 pi times 1 over RC. Under the assumption that FM is very large, okay, and secondly, for the low frequency, for the high frequency pole, this can also be approximated as 1 over 2 pi times Fm V over D times L. And specifically for Bach topology, right? We can basically write out the expression for Fm. So remember, previously we had derived. Here I just use it. So for Bach, since Fm for Bach equals to 1 over Ma, which is the slope of the artificial ramp, plus M1 minus Ma over 2 times the switching period. And for Bach topology, right, we know that M2 is the slope of operation mode 2, so which equals to the output voltage divided by the inductance. And also we maintain a relationship, right? M1 times D equals to M2 times D prime. So by combining those two, we can find out the expression for M1. Then we insert those three expressions into the approximated high frequency pole expression. So you will see that high frequency pole will be equal to switching frequency, which is 1 over Ts here, right? Switching frequency divided by pi times a coefficient which is M1 plus M2 divided by 2Ma plus M1 minus M2. And furthermore, we can reduce this fraction, right? Because we list the relationship between M1, M2, and D, right? So this can be modified as Fs over pi times 1 over 1 plus 2D times Ma over M2 minus 1. So now let's look at the result here, right? So basically, this circled part shows that how close is the FHF, high frequency pole, to the switching frequency, right? So this means that the high frequency pole is near or higher than the switching frequency, which is really high frequency pole here, right? So which agree with our previous arguments on the CPM controller. Okay, now let's erase the right-hand side of the blackboard to continue to derive the other transfer function. Okay, we have erased the blackboard, and also I have copied the control to output transfer function results to the left corner of the blackboard. Now let's continue to look at the line to output transfer function. So again, we first list the results we derived previously. So line to output GVG CPM is equal to the ratio between output voltage and the line input voltage, small signal, under the condition that injection source is 0. VZ equals to 0. And meanwhile, the controlling signal is 0. IC cap is 0. So this will be a long fraction. So I just copy it to here. So GVG minus FM FG times GVD plus FM times GVG GID minus GIG GVD. And the denominator is 1 plus FM times GID plus FV times GVD. Specifically for buck converter, we'll have this part, the bracket part equals to 0. So GVG GID minus GVD GIG equals to 0. And also for buck, we learned that the coefficient of FV equals to 0. So that the line to output transfer function can be much simplified. So we can derive that GVG CPM will be equal to, so the fraction numerator is GVG minus this term FM FG times GVD. So here is 0. And denominator will be only these two parts, right? 1 plus FM GID. And next, we can insert the expressions for GVG, GVD, GID into the formula on the right-hand side, right? So basically, this will be equal to GVG is D over denominator S minus FM times FG GVD equals to V over D times denominator, right? Divided by 1 plus FM GID, which is here, V over dr times 1 plus SRC divided by denominator S. Then we can simplify this fraction by multiplying both numerator and the denominator by the den S. So that GVG CPM equals to, so this is eliminated, this is also eliminated. So D minus FM FG V over D. And here is denominator S plus FM V over dr times 1 plus SRC. So basically, you will see that the denominator of the line to output the transfer function is identical to the denominator of the control to output the transfer function. So this means that they share the same quadratic form response, right? Meaning the same omega c and the same quality factor quality factor. So basically, we can also normalize this line to output transfer function. So you will see that normalized results is GVG CPM equals to GG0 divided by 1 plus S over omega C, QC omega C plus 1 over omega C square, S over omega C square. So omega C and the QC are exactly the same as the omega C, QC here. And so the only thing we need to care about is the GG0, the DC gain, right? So we can compare those two formulas to find out the expression for GG0. So basically, GG0 equals to D times the fraction of 1 minus Fm Fg times V over D square divided by 1 plus Fm V divided by dr. So furthermore, we can try to introduce FM for buck converter to here, right? So we can obtain the results with MA/M2. So this will be equal to GG0 equals to D times, the fraction is modified to be 1 plus Fm V over dr. And numerator is changed to be 2 times MA minus M2 divided by 2 times MA plus M1 minus M2. So you will see that this part highly depends on the relationship between the MA and M2. MA is the artificial ramp slope, right? So if we choose the slope of artificial ramp to be equal to the 0.5 M2, which is indeed a common choice for MA, because if MA equals to 0.5 M2, we can ensure that the system is stable over the complete duty cycle range from 0 to 1, right? So if this is the fact, then you'll see that the DC gain will equal to 0. So this means the cancellation occurs. Cancellation occurs, so it means that the line to output transfer function equals 0, right? So the line disturbance will not affect the output signal. So which is actually a good feature for the CPM controller. Okay, so in this section, we have evaluated the transfer function of the buck topology operating in CPM. So we can see that the CPM controller has simpler dynamics with the high frequency pole pushed to be higher than the switching frequency. And also we can adjust the slope of the artificial ramp to adjust the dynamic response of the CPM controller.